In this video, I'm going through the hospital readmissions project. This is the same sample project that you can find on the SOA's website. I'm going to start by organizing the windows so that I have RStudio, the Word document, and the project statement. I'm going to first read through the entire document from beginning to end. On the actual exam, they will give you a printed copy of the project statement, which you can keep with you before you actually start the exam. So you can read through the project statement before your clock starts ticking. That's assuming that Prometric will keep the same format that they had at the last sitting. So the business problem is predictive models for hospital readmission rates are in demand. And so there's this incentive in order to be able to predict accurately which patients are readmitted. The current approach is called a LACE index, and your task is to build a model that has a higher AUC score than the LACE index. This is a partially completed analysis in that they try to help you out by giving you starter code. And then they have a list of specific tasks to give you. So I'm going to start at task 1. 6 points. Use graphical displays and summary statistics to determine if any of the variables should be transformed, and if so, what transformation should be made. Do you recommend transformations? If so, delete the original variables. So go right down to task 1. And I do need to make a change because I need to load exam PA data. And I'm going to load the tidyverse. So the target variable here is the number of ER visits. So you can see here that it's right skewed. ER visits is a counting variable. And so it's reasonable to leave it as is because it is just an integer. You can also look and see that there are only 9 different values. So in this project report, I'm going to summarize this. So let's look at the graph. The target variable, ER visits, I should say this is not the target variable. This is simply the number of ER visits. Number of ER visits is a counting variable that goes from 1 to 9. Because this has discrete values, no transformation is applied. Let's look at the other variables. We have length of stay. You can see this is right skewed, and it's always positive. Length of stay is strictly positive, right skewed. So if we apply a log transformation, it is more symmetric. We apply a log transform to make this more symmetric. Other variables were age. So we just have age and risk score. The age distribution shows that most patients are older, over 65. So the solution says that they should add an indicator variable for patients who are over 65 because you are supposed to know that that is the eligibility cutoff for Medicaid. However, most people, I'm assuming, if they don't have a health background, are not going to know that. So I'm just going to take a log transform, which is I should say this actually was the log of age. Oh, this was age itself. This was the log of age. Aha. And does it even make sense to apply a log transform? It's making the distribution more symmetric. So in this case, I would say yes. So this is actually, I don't think this needs a log transform. I think this is already somewhat symmetric. This is already approximately symmetric. There is a there are more patients who are over 65 than who are under 65. Applying a log transform does not correct for this, and so the variable is left as is. Okay, now we just need the risk score. This is definitely right skewed. The risk score is positive, right skewed, and so a log transform was applied. This makes the risk score distribution more symmetric. Okay. Question, and they said to remove the original variables. So let's create a new copy of the data set where say log risk score is equal to log risk score, and then log length of stay is equal to log length of stay, and we're not transforming age. And now we want to deselect the original variables. That means that we just put a minus sign in front of the select. And that looks good. Task 2, examine the relationship between DRG class and DRG complication. So it appears that there is an overlap in the two variables. Examine them and determine if it makes sense to combine them in some manner. If so, create a new feature and delete any variables that will not be used. So DRG class, the diagnostic related group, there are 3 categories, and complications with 5 labels. So you can see that the goal of the question here is to make the model variables simpler so that when you build a model, it will have fewer coefficients. So here, you can see that the DRG class is either medical or surgical, and a complication is also medical or surgical. So there are 6 patients here who have a surgical class, but a medical complication, which does not make sense based on the definition from the data dictionary. So there are 6 patients that have a surgical class, but a medical complication based on the data dictionary. These do not make sense and appear to be an error, and so are removed. And that was not the right code. There it is. Okay. And now we have to create a new variable which simplifies these 2 columns down into 1 column. So we're just going to call this class, and we're going to use a case statement. It's going to be based on DRG class, when this is med, and when complication is equal to surgical or medical MCC, then we're going to say med. And then I'm just going to do this for each of the different combinations of the 2. So when this is med and this is med NOC, and this is other, this will be other. And then when this is surgical, whoops. This is when class is surgical and complication is medical. Well, it doesn't really matter because we're going to delete these. So let's do that right now. Filter. And we want to exclude the records where class is surgical and complication is medical. And so these will disappear. And then surgical and other. Go to other. Surgical and surgical MCC. Go to surgical. Surgical, surgery, NOC. We'll also go to surgical. And else we'll go to other. Okay, and now let's count this new variable class to see. So there's medical, other, and surgical. Now I want to save this as the original data. And then I want to drop the original variables. So I want to select minus drg class drg complication. Okay. And now I have to document everything that I did. We created a new variable, which is one of three categories: medical, surgical, or other, depending on the values of drg class and drg complication. The number of records for each category is below. Okay, let's just see. Create a new feature and delete any variables that will no longer be used. Task 3. Use observations from cluster analysis to consider a new feature. Okay, so I need to look at the R file to see what they are referring to. So here they give us some very complicated code. They want us to interpret it. Code is provided to perform cluster analysis from 1 to 12 clusters. Construct an elbow plot and create a new variable based on a selected number of clusters. That variable will need to be retained. Potentially added taught the data frame. Okay, so you can see that they define end start to be 1, and then they say cluster vars are length of stay and age. We know right away that we took a log transform of length of stay. We did not transform age, so we'll have to change this. And then for each of the cluster vars, apply scale. Now, this is because when you apply a k-means algorithm, if you do not scale the variables, the variables which have higher variance will get more of the weight in the algorithm. Because k-means is based on a distance measure, on a distance measure, Euclidean distance measure, we needed to scale all variables before applying k-means. We used the log of the length of stay and age variables. And here you can see that they're using this function k-means, which is taking in these variables, these centers, and this starting value. To get more detail, you can look at the documentation. So you can see that X is the data matrix, centers is the number of centers, and start is how many random seeds should be chosen. So for now, we're just going to leave it at 1, but we just note what it's doing. And then there's this variable explained data frame, which takes the between sum of squares divided by the total sum of squares. So let's just change this to log length of stay, and then run everything down to here. And you can see there's a plot, and on the x-axis is the value of k, which you've chosen from 1 to 12. And on the y-axis is the percent of variance explained. So when the k is equal to 1, it means that all of the observations are in the same cluster, and none of the variance is explained. When k is equal to 12, it means that there are 12 different clusters, and that about 80% of the variance is explained. So you don't just want to, so for k-means, you have to make a selection of k to decide how many clusters to use. The suggested method is to look for an elbow and then choose the value of k, which is at the corner. However, it doesn't really look like there's a clear elbow here, so choosing a value between 4 to 5 or 6 would be sufficient. However, this was just using n starts is equal to 1. So let's just turn this up to a higher number. Not too high because this will be on a Prometric toaster computer. And so runtime will be an issue. So I'm just going to set it to 20 and then recreate this plot. As you can see, it's still fairly slow, and this is on a pretty fast computer. So I want to just include this graph and then summarize everything that I just explained. Okay, so what I talked about, the number of starting values, and k-means is most reliable when using a high number of starting values and then taking the average over all iterations. This helps to prevent the algorithm from getting stuck at a local minimum. To fix this, I set n start up to 20, where it was originally 1, so that the results are more reliable. The graph below shows the percent of variance explained against the value of k. This value of k needs to be chosen by the modeler. A good strategy is to choose the value of k where the plot elbow bends, which is at about 4 to 6. We chose k is equal to 4. And then I've included the graph. So here I want to use 4, so I want to use km4 as the cluster. And then they say cluster vars is equal to the cluster. So basically they've stored this as a numeric value. So then they create this plot, which you need to change so that it uses the log of length of stay. And I'm just going to include this. So what this graph is showing is the length of stay on the y-axis and the age on the x-axis. And the color represents the cluster which that patient was put into. So patients who have a young age and a high length of stay are in this green group. Patients who have an older age and a lower length of stay are in this red group, and so forth. The graph below shows how each patient is put into one of 4 clusters. Let's just look at the project statement again to make sure that I'm not missing anything. Run the code on these 2 variables. Select the best number of clusters, create a factor that could be used in place. Your assistant has provided code that illustrates how to do this. Okay, I've done this. Task 4. Select an interaction. Select one pair of features from among gender and race, ER and HCC risk score. That should be included in the interaction variable in the GLM. Do this first, proposing 2 variables that are likely to interact, and then one using the supplied function to graphically confirm the existence of an interaction. Continue until a promising interaction has been identified. Include your selected interaction when constructing a GLM in the following tasks. So, the following code will help you determine if interactions are present. So this is using gender. It's looking at an interaction between gender and race. And you can see that for each race, and with these one of 4 plots, you see the readmission status by gender. If there was a really strong interaction here, these percentages would be very different for some races than they are for others. Here it looks like across each of the race categories, the percentage is about the same. So that means that there is not a strong interaction. we inspect two possible interactions, race and gender, and ER and risk score. Let's just define what an interaction is. An interaction occurs when the value on the effect of a variable on the response is different depending on the value of another variable. We inspect two possible interactions, race and gender, ER and risk score. Race and gender do not appear to have a strong interaction. The below graph shows the percent of readmitted patients across each race and gender bucket category. If there was a strong interaction, then we would see that this readmission percentage would be different for some graphs than it would be for others. Okay, and the other possibility is readmission status and HCC risk score. So if you recall, this is actually the log risk score. Don't remember what the name of that is. Yes, it's just log risk score. So here you can see the number of ER visits is each plot, so from 0 to 9, and the readmitted status is either 0 for not readmitted or 1 for readmitted, and the risk score is the value on the box plot. So for instance, if a patient never had a ER visit and they have a readmitted status of 1, they have a higher risk score than if they were not readmitted. But that changes depending on the number of ER visits. So for instance, if these patients here who have 5 ER visits, the patients who were not readmitted have a higher risk score than those who were. So this relationship changes depending on the values of ER and risk score. So that indicates that there is an interaction. The interaction between risk score, the log of the risk score, and the number of ER visits appeared to be stronger. Below, we see that the average risk score changes depending on the joint values of ER and log risk score. This suggests that we should add this interaction into the model. Okay, now we're moving on to the construction of a GLM. Task 5, select a link function. So let's first look at the R code. So task 5 runs a GLM. It assumes that train and test sets have been constructed. So I have to go back and get the code which creates the train and test sets. And all that this does is it splits the data up into 75% training, 25% test. And you can see the average readmission status is approximately the same between both sets. So I'll just say this. First, split the data into training, 75%, test, 25%. The readmitted patients had the same percentage between the training test sets. Now we have to select a link function. So this code that they give you does all of the work. Your task is to interpret it. So they say GLM logit is equal to a GLM where readmission status uses all variables plus an interaction between gender and race. So the first question is, do you want to use this interaction? In our case, we want to use log risk score and ER. I'm also going to, I don't like to name my models specifically. I like to use generic names so that I can copy and paste code. So I'm just going to call this GLM. Additionally, I want to check to see what variables are actually in the model. So if I look here, I can see that there's gender, race, ER, age, log risk score, log length of stay, and class. Okay. So the question is, select a link function. And they give you several different link functions which are possible. So basically, you just have to fit 5 different models and then evaluate each of them. Identify the best choice of link function. So how do you define best? Explain prior to fitting the model why your choice is reasonable for this problem. Fit your choice plus one alternative and compare your results. You can switch the alternative if it performs better. Okay, so you have these different link functions and they want you to just explain what they are. Explain what a link function is. Okay, so the logit is the canonical link function for the binomial distribution. This transforms the linear predictor from the range of all numbers from the range of continuous numbers to a probability from 0 to 1. The results of a logit are not easy to interpret. However, because this model is aiming to maximize predictive power, the AUC, this interpretability is not an issue. So they essentially just want you to have facts memorized and then be able to retrieve them on command. The probit is the inverse CDF of a standard normal random variable. This is more interpretable than a logit Cauchit. Not even sure if that's the correct spelling. C-A-U-C-H-I-T. The Cauchit link is much less common than the logit or probit. And the complementary log. And I missed the log link. So the log link allows for values outside of the range of 0, 1. So this is not tested because we want a probability. The Cauchit link is much less common than the probit. We will fit a model and evaluate the AUC on a test set. And really that's the same with the log. So I'm just going to see log is much less common than the logit or probit. We will fit a model to evaluate the AUC on a test set. So identify the best choice of link function. Explain prior to fitting model why your choice is reasonable for this problem. Fit your choice plus one alternative and compare your results. Okay, so here's our code, which I'm just going to make a little bit cleaner. So I'm just removing the word logit everywhere because I want to be able to just copy and paste. Okay. And let's just see the AUC 7451. And let's just make sure we have all the variables. We have gender, race, ER, age, log risk score, length of stay. Okay. Now let's do this for the other variables. We just have to change this link function. And we only care about the AUC. Really, all the other variables, that's the only statistic that the question is asking for. So this is interesting. The AUC is identically the same identically the same, 7451. 7451. You can look at the coefficients, see that they're slightly different. But the AUC is the same. And now what do we need? Logit, probit, cotchit. 7448. That's a little bit lower than the other two models, which is worse. And we're not going to test the log. C log log is 7451. So this is actually the same as the probit and logit. So to summarize, the logit and probit models have the highest AUC, which is best. And so these two are considered. The C log log and cotchit. The C log log also has a high AUC. However, this is not as common of a model of a link function and is more complicated. And so we are not considering, we are only considering the logit and the probit. The cotchit has a lower AUC and so is not being considered. Now, let's just see if we got everything the question was asking. Identify the best choice, explain prior to fitting why your choice is reasonable, fit your choice plus one alternative. With respect to task 3, use the original two length of stay and age variables, or the transform versions, and do not use the feature which you created from the cluster analysis. Okay, we haven't done that. Do use any transformations from task 1, any replacement variables from task 2, and the interaction from task 4. So let's just double check. We included the log of length of stay and the log of the risk score, and we used the new class variable here. Okay, looks good, and we're not using the cluster feature. Task 6, decide on the factor from task 3. Fit an additional model except drop length of stay and age, or use their transformed versions, and add the variable created via clustering. Okay, so I need a new data set. So I'm going to say train cluster is equal to train and select minus log length of stay and minus age, and then mutate. let me think for a minute. What do we have? Where is the actual cluster? The cluster variable is called length of stay age cluster. So this is based on the full data, right? So if you look at the length and compare that to the dimension of readmission, you'll see that it's the same. So in other words, we need to assign this readmission cluster is equal to mission, and mutate cluster is equal to this cluster. And now we need to create a new training and a test set. So call this train cluster, test cluster, and it will be based on this data. Let's just look. So here's readmission status, cluster. Yes, okay. And we want to deselect the length of stay and age columns. Let's just check. Okay, so there's no length of stay and there's no age. Okay. And we're still going to use the interaction here between risk score and ER. We're just going to change the data. And because we already chose the, let's just use the probit link function. There's an error here. Yes, so we want this data to be on test cluster. AUC is 7449, which is worse. Well, actually, 7449, yes, 7449 is worse than the original model. We dropped the log length of stay age columns and replaced them with the cluster feature. We refit a probit model and found that the AUC based on the same test set as in task 5 was worse. For this reason, we are not using the cluster feature, but instead the log length of stay and age variables. Okay, task 7. Select features. The remaining model construction task is to remove variables to prevent overfitting. One approach is to use a function such as step AIC on the current set of variables. Now, one critique that I have here is that simply removing variables does not prevent overfitting. The only way that you can measure overfitting is if you are evaluating the performance using a holdout set or cross-validation in order to see the difference in model performance based on the training set versus the test set. It could be this is a simplification, is what I'm trying to say. But when I'm taking the exam, I have to suspend judgment like this and instead just do whatever the question is asking me to do. One approach is to use a function such as step AIC on the current set of variables. However, for factor variables, this function either retains the variable with its existing levels or removes the variable entirely. It does not allow for the possibility that individual factor levels may be insignificant with regard to base level, and hence could be combined with it, or significantly different, from other levels, in which they could be combined to a new level. Simplify the model by removing features entirely or combining factor levels as appropriate. Use an approach that relies on hypothesis tests or information criteria. So they're just saying use step AIC when you've converted the factor variables to binary variables. And then calculate the AUC and see if it's higher than the least index of 0.75. Okay, so this is task 7. So we want to use step AIC. Well, first, let's make sure that we have the correct model object. So we want to go back to whichever model. We could either use the logit or we could use the probit. They both have the same AUC, 7451. So it honestly doesn't matter. I'm just going to use the logit because logistic regression is more common. So it might be easier for other people to understand. Now you could also just use the probit in this case. It would not make a significant difference because the performance is the same. This is just my choice. Okay, so now I have a model object GLM here, and I want to use step AIC GLM. I don't actually remember the syntax for this, so I'm going to look at the documentation. It takes an object representing a model, and a scope to define the range of models, and it has direction, cape, and K. So let's just run step AIC. And it says I can't find the function. I have to load the library mass, I believe it's called. Yes. And then it is going through and trying to simplify the model by adding or removing variables. I should say, yes, by adding or removing variables. So it starts out with all variables, and then it is removing, what does it remove? It removes race first, and then it removes gender. And it keeps going, and eventually it only contains class, log length, let's say, and age and risk score. And the AIC starts out at 33,000 and continues to increase to 37,000. So in this question, our goal isn't just to simplify the model. We want to improve the predictive power, right? And they give us this code here to convert the factor levels to binary values. So this is the first step before we actually run step AIC. Whoops. So this takes in factor names, ER and H. I'm confused here. Why does this say factor names are ER and H? Because age is clearly not a factor. If you look at the actual data, the factors that we have are gender, race, and class. So this is going to take factor names and convert them to characters. Okay, well, these are already characters. You can see here, so I don't need this part. And then binarizer is dummy vars, and it takes factor names and then creates dummy variables. So I'm not going to change this. I'm going to see if it actually works. So these should be the factor names. So gender, race, class. And it says contrast can only be applied to factors with 2 or more levels. I suppose class, actually not sure why that works, why that doesn't work. So if you run into a problem like this on the exam, and let's say that you can't diagnose this in time. Let's say that you're, let's just read this. This chunk performs binarization. Note that it is set to full rank false. This creates binarized variables for each factor level. If set to true, it will leave one out. Note that the new variables are placed in a new data frame. It can be attached to in the existing data frame. Whoops. I actually don't like this code. So I'm just going to quickly create my own dummy variables. This isn't, so I need dummy variables for gender M. So gender M is equal to, else gender is equal to M. It's 1 or 0 if not. And then race, how many different race levels are there? Let's see what happens if we remove race from this model. Nope, it still does not work. Okay, well, I guess the question is, should race be included in the model? Does it really make sense? I would say no. I'm just going to say that because we're supposed to be selecting features, right? So we can choose well, they don't say to remove variables if you if you think that they shouldn't be in the model. So I just say race. No, I'm not going to include race. I'm just going to say While race is included in the model, there could be issues related to privacy and legal concerns. And so to be safe, conservative, we drop the race variable from the model. This also makes our lives easier. Okay. So we're getting rid of race, so we just need a factor level for class. So I need class other is equal to if else class is equal to other 1 or 0. Class surgical. Class is equal to surgical. Class medical is equal to, okay. So we have race and class. The other variables are just numeric. And I'm just running a summary to see that there are no NA values or other confusing issues. And I wanted to deselect the original factors, gender and class. So I'm going to call this readmission dummies and this error is because I've loaded the mass library, and mass has a function called select. I want to use the function from the dplyr library, and so I use the : to tell R which library to use. Okay. And now we have these dummy variables. Now I'm going to recreate the train and test sets quickly. I'll call these train dummies, test dummies. And I want to use okay. Finally, we have the data with dummy variables, and now I want to refit the model using these dummy variables. So I just need to change the data to train dummies and test to test dummies. Okay, now I can look at the GLM and see the p-values for each of the different classes. And if you look, you'll actually see that the coefficient here for class med is NA. Now that's because it's an overdetermined system. So if class other is 0 and class surgical is 0, then automatically you know that class med is going to be 1 because each patient has to be in one category, right? And so that means that the features are a linear combination of each other, which means that the model matrix is rank deficient, which results in those null values in the coefficients. So I've removed class medical, and if I refit the model, I will see that this is no longer an issue. Okay, now let's look at the AUC 7451. Hey, that looks it looks to be the same. So in other words, there was no improvement. Well, there should not be actually, because we haven't run step ASE. So that's good. That's a good check to see that the model is identical to what you had before. Now when we run step AIC on this, we should get better performance. Okay, so the final model is right here. So they're using loss other, age, and risk score. So let's just refit another model that has these coefficients. So we just want the formula from above, which is log loss plus class other plus age plus log risk score. Now let's look at the AUC. 7453. So we've made some improvement. We first, after removing race, we created dummy variables for the gender and class columns. We used one fewer dummy value than ren factor level, so that the model matrix was not rank deficient. We then ran step AIC to remove any additional variables. After evaluating, after running, now it might be a good idea just to include everything here. The result is below. You can't lose points for including more output than is required. So I'm going to use the shortcut Control right or left bracket in Microsoft Word to change the font size. And go back to our normal font size. This simplified the model to only use log loss class other age log risk score as predictors. The AUC of this model was better. 7453. Then the other models. 0.74. What is the lace index AUC? That's what we're trying to fit, right? The lace index AUC was 0.70, right? This is better than the lace model of 0.70, which was the business objective. Let's also get the summary from this model. the p-values are all greater than 0. Okay, let's just see what else they wanted. Okay, this will be your final form. This looks good. Task 8, interpret the model. Run the selected model from task 7 on the full dataset and provide output. Interpret the results in a manner that will provide useful information to the hospitals. Okay, so the first step is refit the model on the full dataset, right? So I just want to change my data to readmission dummies. So I've trained it over the entire data set. I don't need any of the predicted values because I'm not looking at the performance. I just care about the coefficients. So here I'll include everything. I refit the model over the entire data set so that the variance of the results is lower. Models with a larger sample size are more reliable. And now I just have to interpret this. We can see from the signs of the coefficients. Well, I should say because we use a logit link function, we cannot interpret this GLM simply by looking at the signs of the coefficients. What we could do is we could create some average cases and then see how the predictions change depending on the average patient. I'll do this for one. Well, let's just see if they ask. It says interpret the model. Run the selected model. Interpret the results in a manner that will provide useful information to the hospitals. This will be discussed in your executive summary. That's really key because if you don't have some type of interpretable result to talk about in the executive summary, you will lose points on the executive summary, which is worth about 20% of the exam. So it's really important when you design models that you think about the executive summary section. So as I was saying, because this is a GLM with a logit link function, it's not easy to interpret. Fortunately, we only have 4 variables. And so if we just create some average patients and then change the different values, we can see how the predicted value will change. So let's just say example 1. Well, first of all, let's look at just a summary of the variables that are in the model. So we need readmission status, and we need log length of stay, class other, age, log risk score, right? Just these variables, and I want to use dplyr to select. And then I just want to see a summary. That's not that useful actually because these are numeric. So let's look at length of stay, class other, age risk score. Okay, so I can see the average readmission status, percent readmission status. Well, this doesn't matter because this is our target. So the average length of stay is 1.6, average age is 73, average risk score is 0.6. So let's just create example 1, which is equal to a tibble or data frame where log length of stay is equal to the 1.65, age is equal to 73, log risk score is equal to 0.6. And now I just need class other. So what's the percentage of, what's the average percentage? Let's see, count class other. So what is this as a percentage? This is 16%. So 16% of the patients are in the other class is equal to 0.16. Right? So this is our average example. And then we can just get a prediction for this. So preds1 is equal to predict golem example 1. And we want this type to be response. And let's example 1 mutate preds. Actually, let's mutate predicted is equal to predict. No, I'm getting too complicated here. I'm going to keep this simple. Predict is preds is equal to preds1. Okay, and now I just want to copy this and change things. Like let's say that the length of stay for another patient was 3. The log length of stay was 3. Everything else was the same. So let's just first get this output here. So first we look at the average patient. To interpret the model, we look at the change in predicted value when permuting the values of the coefficients of the variables. We start with the average of each variable. I can't copy this as a nice table. Well, I should be able to do this. I should be able to. Huh. Not sure why this isn't copying. Okay. I'll have to figure this out a different way. So what happens if you change the length of stay to 3? Someone was in the hospital for a really long time. What if the age was much younger? What if you were a young patient? Set the age to 20. Or what if your risk score was really high? So risk score is 3. Or finally, what if your class other was different? What if your class other was 1? where most of the time it's not. So let's make sure that we reset these. Okay, so this is average age is 73. And then we make so we want all of these to be 73. This is 73, 73, and then we want risk score to be the average again. So we only change one variable at a time. Okay. As you can see, this is pretty manual. There's not really a science to this. And if this was a real exam, honestly, I would probably not take the risk. I would just move on and start writing the executive summary, because time is really the, if I lose 5 points on this question because I didn't get every point possible out of this one task, that's less important than if I run out of time and can't finish writing the executive summary. So I'm just saving all of these values as these temporary values, which I call t's, and then I'm going to r-bind all of them together. Now, if you want to skip this part, that is totally fine. You do not have to do this. So here you can see the predicted values variable and then change one variable at a time. So for older patients, okay, so for the first patient, this is the older patient. I think this is a coding error because I'm using, because these values are all the exact same. So this tells me that I've done something wrong with the code. So here, example 1, predictions 1, example 1, predictions 1, example 2, predictions 2, example 3, predictions 3, example 4, example 4, predictions 4, example 5, predictions 5. Okay. Okay, this looks better. And I'm not able to copy this. There we go. And this is not formatting as I want it to. I'm going to use a cheat. So I'm going to use function to create an HTML table. There we go. Okay, so based on this, we can interpret the results and see that the prediction increases as length of stay increases for younger patients, increases for older, for as risk score increases, and is about the same for the other class that are in the other class as not. Now here, I'm really just focusing on getting some interpretability. This isn't going to be perfect, but it will at least be more than having an absolute black box. So I look at the length of stay. See, as length of stay is 3, the average prediction increases slightly from 9% to 10%. For younger patients, when you permute age to be 20, the predicted value increases slightly as well. As the risk score increases, as the risk score goes up to 3, the predicted value jumps up to 0.71. And as you change the other variable so that the patients are in the other class, the prediction stays, it's a little bit higher, but it's about the same. And I'll say this age increase is not that, it's only a minor increase. Okay, let's go back to see what else they asked for. Run the model, interpret the results in a manner that provides useful information. This will be the model discussed in your next executive summary. So this question was only worth 6 points, and yet I've just spent about 10 minutes answering it. So really, I would say if this was a real exam, skip this part. Just say that you used a logit link function, and so you cannot interpret the results, and just keep moving. Question 9, set the cutoff. The hospital is also interested in an alternative model to understand the benefits of using your model. They have produced the following approach to evaluate the benefits. Okay, so this is task 9. So in task 9, they want you to set the cutoff value. So the cutoff value is the percentage of, it's the probability value that determines if a patient is counted as a readmission or not. Value is the threshold of the predicted probability that determines whether or not a patient is readmitted, is counted as a readmission. So they give you these different scenarios. Any patient who is readmitted incurs a cost of $25 to the hospital. These numbers have been scaled. An intervention program is being considered such that for a cost of 2, any discharged patient who receives the intervention will not be readmitted. The hospitals are considering 3 options. Do not employ the intervention program, apply the intervention to every discharged patient, or apply the intervention only to those patients predicted by the GLM to be readmitted. The hospital does not currently have information about how the Loess index would perform. Use the confusion matrix from running the model on the full dataset to estimate the cost under each of these 3 options. You should change the cutoff for predicting readmission to optimize the result. Okay, so this is called, so here, I've gone and fit the model to the entire data set, and I've named this GLM, right? And based on this, I want to tune the cutoff value so that the cost to the hospital is minimized. So the first step is I need predictions on the full data set, which is what I have. If I look at my predictions, and I'll see that they're a probability, right? See, there's a distribution of predictions from 0 to 0.6. And if I set the cutoff value at different values, it will change the percentage of patients which are counted as readmissions or not. And they give you some scenarios. So if a patient who is readmitted occurs a cost of 25 to the hospital, so then, so if a patient is readmitted, so in other words, if they're, if they have to go back to the hospital, it costs them 25, right? And here's some code that creates a confusion matrix. You can look at the confusion matrix to see there were 25,000 patients who were not readmitted who were predicted not to, and there were 7,392 patients who were predicted to be readmitted and were actually readmitted. There were 1,000 who were predicted not to be but actually were, and there were 33,000 who were predicted to but were not readmitted. So basically, we want to take this and apply a cost to each of these buckets. So if the patient slips through the cracks and we don't predict them to be readmitted, but they are, that incurs a cost of 25. In an intervention, and if the patient receives readmission, they have a cost of 2 applied to them. So if you have no intervention, so basically they give you 3 scenarios: no intervention, full intervention, and modified cost. And this is a function of the cutoff value, right? And so what you want to do is to create a function called getCutoff, which is a function of cutoff, or I should say it's getCost. GetCost is a function of the cutoff, and it's going to take in the cutoff value, and it's going to return a table of these values, right? So it's going to say no intervention is equal to no intervention cost. Let me rephrase this. I only need modified cost to be returned. Let's test out this function. Get cost of 0.5. So this will return 0.5. Okay, let's take let's just test out different values of the cutoff and see how the modified cost changes. So on the top will be no intervention cost if we didn't predict that any patients would be readmitted. And then on the top would be full intervention cost if we administered intervention to all patients, right? So if we had no intervention, the cost would be 21,000. If we had full intervention, the cost would be 16,000. If we set the cutoff value at 0.1, it's a little bit lower. At 0.2, it's even lower. 0.3, it's higher, so forth. So we basically have a curve. So I just want to create this table. You could create this probably, I'm just going to create this in Excel. I could do this in R, but let's do it in Excel. So here is the cost. Here's the cutoff. So this is 0. This is 0.1. And this is 1, no intervention. So this is no intervention, full intervention. Okay, let's get rid of these. And format. Okay, let's put this into the document. The cost to the hospital changes depending on the value of the cutoff. If we do not administer intervention at all, then the cost is whatever that number was, 210, 255, whereas if all patients are given the intervention, the cost is 161. That seems too low. Why is this 161? It says this is a full intervention cost. Full intervention cost. Which is 4 times the predicted readmit. Now this full intervention cost would be would be the cost of giving it to all patients. So how many patients do we have? So we have 66,000. And how much is it per patient? It's 133. Actually, so a little bit confused as to why this isn't working out quite as I expect. It looks like in this curve, the cutoff should be 0.2. This full intervention cost is lower than I expect it to be, because this is saying that it's best to give the intervention to all patients. For a cost of 2, any discharged patient who receives the intervention will not be readmitted, right? So if I give this treatment to all patients, then the cost would be 2 times the number of patients. 2 times the number of patients would be 133,000. And that's lower than any of these other values. Full intervention cost . Why does this have 4 times the patients who are readmitted? Because this says full intervention cost is 4 times the sum of the predicted readmit, right? So if you predicted that all patients would be readmitted, then your full intervention cost would be 4 times that. So I think this is the answer. I think this should be 26. So 267,104. Instead of 133. I think that's a mistake. The cost is 267,104. So this is saying that the cost per patient is 4. I mean, the code seems to be saying that the cost per patient is 4. The problem here says the cost per patient is 2, which is why I'm confused. So I'm going to go with what the code is saying. Now here, if this is a real exam, I'm going to say this. There was some ambiguity in that the RMD file was using cost equals 4 per patient for intervention, but the project statement was saying cost equals 2 per readmitted patient. These calculations are using the assumption from the RMD file. This suggests that the value of the cutoff is 0.2. Okay. I'm also going to include the confusion matrix. So when I set the cutoff to be 0.2, I want to see what the confusion matrix is. Here we go. The confusion matrix is below. The confusion matrix when using this is below. Okay. Task 10, consider alternative models and model construction techniques. I'm going to give you specific models to look at. So they want lasso, classification tree, and a random forest. So I want advantages or disadvantages. Advantages to a lasso are that it performs variable selection. It has greater predictive power due to penalty term shrinking the value of the coefficients. Disadvantages. Well, it has all of the. It's just as predictive as the GLM. Handles interaction term with what we said was ER and log risk score, so forth. Disadvantages are sensitive to outliers, requires variables to be scaled before fitting, and in our library does not support alternative link functions such as probit. Only logit, I believe. Or non, yes, I believe this is right. No, I don't believe it's the link function. I believe it's the response family. If I look at the GLMNet library and see it's Gaussian binomial or Poisson. So so this doesn't matter. Classification trees. easy to interpret. I can add this to the lasso. Can be converted to a spreadsheet. Handles missing values, interaction effects, non-linearities, disadvantages, low predictive power, sensitive to overfitting, predicted values are step-like and can change drastically from small changes in the inputs. Random forest. Advantages. Higher predictive power. All of these advantages from trees. Easier, less risk of overfitting. Whoops. Disadvantages. Less interpretable. Not an issue. Less. This doesn't really matter in this problem. Less interpretable. More training time. More compute resources. Okay. Moving on. Executive summary. 20 points. And they also say indicate the advantages and disadvantages for the business problem. So for the business problem, advantages are it forms variable selection, which makes the model easier for the hospitals to use. It's easier to interpret, which gives healthcare providers insight into patient health. Can be converted, and disadvantages are sensitive to outliers, requires variables to be scaled prior to fitting. Classification tree. So if I was fitting this for a hospital, it would be easy to interpret, which is good for a non-technical audience. Disadvantages are low predictive power. Random forest, higher predictive power, handles missing values, handles interaction effects. Disadvantage, less interpretable for less interpretability. Means that the hospitals will not be able to understand why certain patients are predicted to be readmitted. So basically, they don't just want you to talk statistically, they want you to speak to the business outcome. They want you to say why it could be an advantage or disadvantage from a business perspective. And I don't know why I'm spending time on this formatting, because This formatting is not graded here until we get to the executive summary. So this is the part of the report that really matters. This is the 20 points. This is the difference between an 80 and a 100, between a 100 and a 60. You've raced through hours of the exam just to get to the executive summary. Your executive summary should reflect the information provided in your tasks from 1 to 9. Your executive summary should include a problem statement and a coherent explanation of all the steps leading to your recommended model and conclusions. So I'm just going to go through each task and summarize. So let's start with a business problem. So hospitals lose revenue when patients get readmitted. The Centers for Medical CMS, Medicare, and Medicaid CMS has a model called LACE, which predicts which patients get readmitted. This helps hospitals to reduce their readmissions and increase revenue, which increases profitability. Being able to more accurately predict patient readmissions there helps the hospital to remain profitable. Using a predictive model, we can predict better than LACE which patients will be readmitted. AUC is 0.74 versus 0.70. Here, AUC refers to AUC is a statistical measure of performance, of predictive power, where a higher value closer to 1 is better. We started with data on hospital readmissions. For each patient, we had information on the length of prior stays, their age, health status, or risk score, as well as their gender, their race, and what else? Risk score, class, as well as medical history. So using 7 predictors, which were related to whether or not a patient would be readmitted, we identify the leading cause. We built a model to predict these readmissions. Okay, now I just want to go through all of the tasks. So first we looked at we started by looking at statistical graphs of the variables and made adjustments so that the model will be better. We applied a log transform to skewed variables, risk score, and length of stay, right? Let me see, where did we apply the log transforms? Length of stay and risk score. We simplified. We found 6 patients which were outliers in that they were coding errors. We removed 6 patients who were apparently coding errors due to their class being different than their complication status. Their medical class. What else did we do? We simplified the class variables. We then simplified the medical class and complication status down into a single variable. We considered we used an unsupervised learning technique. Now we tested a clustering algorithm which further simplifies down the age and length of stay variables into a single cluster. This did not improve the model when we tested it on a holdout set, and so it was not included. We used a k-means algorithm, which is a simple clustering algorithm that puts each member into a distinct group. We fit several, let's just start at a high level. Generalized linear models are a flexible and powerful predictive modeling technique that relates the response to the values, relates the readmission status to the levels of several variables at once. I also have to consider an interaction effect. We also considered interaction effects, which occur when the effect of a variable changes depending on the level of a different variable. We tested out race and gender and risk score and ER visits. Based on statistical evidence, we found an interaction between risk score and ER visits, which was used in the model. And we then split the data into training and test sets so that the performance would be an accurate measure of the performance in the real world. A model was evaluated based on blind holdout data. And we used several different GLMs. So we considered several different GLMs, and based on statistical tests, we chose the one which had the most predictive power. We, due to potential legal or ethical issues, we did not use the race variable in the model. Now I want to just summarize my results here. We found that the readmission, there's a risk of readmission can be broken down into 4 main causes. The the probability of readmission changes depending on the following variables. It increases as length of stay increases for younger patients, increases for a risk as risk score increases. It's about the same for patients that are in the other class or not. So, okay, what else did we do? So then we considered the cost complexity tuning. Because the goal is to maximize revenue, we took into consideration the different scenarios and chose the model which had the highest, which had the lowest cost. if your hospital had no predictive model, then the costs based on these patients would be 210, 225. If when you know that a patient is likely to be readmitted, there is a preventative treatment that providers can administer. If you apply this to all patients, the costs would be 267, 104. This predictive model has the lowest cost of 170,889. This means that by using the predictive model and only intervening for patients that are likely to be readmitted, your costs can be reduced. Okay, so that's through task 9. And you can see we have just on the executive summary, you have about 600 words, which is good. This isn't the highest quality of writing. The main point, however, is to include all of the information needed. And I'll go through and quickly do a spell check. And at this point, I would save my work and I would submit whatever I had. I would upload it to the Prometric computer so that in the worst case scenario, I have submitted something, right? And then I would go back with whatever time I have left and look through and just see if I've included everything. Is there something missing? So in question 1, use graphical displays to talk about your transformations. I did this for length of stay, for ER. We apply a log transformation. The age distribution doesn't get transformed. The risk score distribution gets transformed, okay? Task 2, examine relationship between DRG class. I've done this. Use observations from cluster analysis to consider a new feature. I explain what k-means is. I say that I use nstart 20, and I say that I chose k is equal to 4. And you can see that there are 4 clusters here. This is cluster with 8 groups. This is really cluster with 4 groups. So let's recreate this just in case they were to take points off for something such as a label on a graph, which is entirely possible. I'm not putting it past the SOA.